Hello, everyone. Welcome to this, the first in this series of lectures that ISAS is presenting. I'm Dr. Eileen Betzenhauser, and I'll be the moderator today. Can everybody hear me? Chat if you can't. Okay. So I'll be introducing our speaker in a moment, but first we need to cover a few things. Please remain muted with your video off during the presentation. Questions are encouraged, but please use the chat feature. We'll compile the questions and then our speaker will answer them as she's able to at the end of the presentation. The contents of this presentation reflect the view of our speaker and do not necessarily reflect the official views or policies of the Illinois State Archaeological Survey, Prairie Research Institute, University of Illinois, or sponsoring agencies. So as I said earlier, my name's Eileen. I'm the field station coordinator at the Illinois State Archaeological Survey's American Bottom Field Station, located in Collinsville, Illinois. The survey, also referred to as ISAS, is a division of the Prairie Research Institute at the University of Illinois. With about 70 full-time archaeologists and support staff working throughout the state, we are one of the largest archaeological research institutions in the US. ISAS has a state of Illinois mandate to provide research, scientific expertise, and objective data that benefit the environment, economy, and people of Illinois and beyond. Part of our mission is the dissemination of archaeological knowledge about the past to our peers and especially to the public. And in that spirit, we're offering a series of webinars this winter and into next spring that highlight our research and upcoming projects. So today we're pleased to welcome our first speaker, Dr. Caitlin Rankin. Caitlin recently joined us at the American Bottom Field Station and serves as our resident geoarchaeologist. Caitlin has long held an interest in anthropology that grew from her participation in an archaeology field school while in high school. During her undergraduate studies at Beloit College in Wisconsin, geologists were able to lure her to the environmental side of archaeology. Caitlin recently completed the doctoral program in anthropology at Washington University in St. Louis, where she worked with T.R. Kidder. Through her studies, she gained field experience throughout the Midwest and beyond. For the past 6 years, her research has focused on how the Mississippian people who lived at Cahokia Mounds near present-day St. Louis, Missouri, interacted with their environment by using soils and sediments as proxies to reconstruct past environments. This grant-funded research earned her the Richard Hay Award from the Geological Society of America. So please join me in welcoming Dr. Caitlin Rankin.
Okay, everyone can hear me? I guess so. I can't hear if you can or not. Okay, so I guess I'll go ahead and get started since I don't hear any complaints that you can't hear me. Today, as a little outline of what I'm going to be talking about is, first I'm going to start pretty general and then get into some specifics. A question I get a lot, since geoarchaeology is such a very specific specialty within archaeology, a lot of people ask me, how I got into geoarchaeology or why. So I'll kind of go over that and then, do a general what exactly is geoarchaeology, talk a little bit about the history and the tools of the trade, and just kind of show you what everyday life looks like as a geoarchaeologist. Then I'll get into the specifics. I'm going to talk about a project I did previously at Cahokia Mounds in Illinois, which involved using elevation data from buried soils to create a 3D model that reconstructs what the landscape looked like whenever people lived there between 1000 to 1400 AD. And then I'm going to follow up and talk about my future research plans here at ISAS to kind of take this model and expand it to a regional-wide model that is going to create what we call a pre-Columbian paleo-topographic model. And so we're hoping this will be helpful to other archaeologists working on environmental human interactions, but we also hope it will be helpful for land managers who are doing some watershed and wetland restoration projects in the bottomlands. And finally, I think we have some time for some questions. So that's going to be the outline for the next 40 minutes or so. We're going to try and keep under an hour. Okay, so why geoarchaeology? I feel like most archaeologists kind of have a specialty that they're interested in that has to do with, material culture. Like they like the ceramics or they like the stone tools. I didn't like any of that. I was never really interested in material culture. For me, it was always about the field work, and my favorite thing was, drawing a soil profile and looking at soil. And so geoarchaeology is kind of that perfect use of my kind of passion about, looking at soil, and then also my interest in, how past people interacted with the environment and how we can use that knowledge to kind of help inform modern issues and modern strategies to present problems. Right, so that's why I like geoarchaeology. And what is geoarchaeology exactly? So geoarchaeology is when we use geologic methods in archaeological applications or to answer archaeological questions. So I have some examples. So one would be if we use geologic methods like XRF, paleomagnetism, or petrographic thin section analysis to determine where lithic material is coming from that people used for, stone tools. So that's one example. Another is using geophysical techniques. Ground penetrating radar is a really popular one to either find or delineate the extent of buried archaeological sites. This is a great method because it's not invasive and it's not destructive. So we can get an understanding of, what's happening below the surface without actually digging it up. Additionally, we can use just methods in stratigraphy, sedimentology, soil science to help understand archaeological site formation, to understand how the site became buried, to understand what happened to it, after it was deposited, and also to understand what the local environment looked like whenever people were actually living there. And that's really the part of geoarchaeology that I really do. And then additionally, we have people who do geochemistry, perhaps to, get a better local baseline or local understanding of what local paleo-environmental conditions were like. Right, and so at a scale that's a little bit more relevant to archaeology than say, ice core data. We can get something a little bit more local. And also just geologists are really good experts in dating things. They have a lot of different methods that we don't use very often. So they can just be really helpful in helping us determining like how old something is. So a few examples of what geoarchaeology is. And in terms of the history of how it came to be, I'm only going to talk about North America because got to break it down somewhere. This could be a little bit different in, Europe or Africa. But geoarchaeology, the integration of geology and archaeology, really has its roots in trying to determine the antiquity of man in North America. So really trying to figure out how long ago people first came to North America. So whenever archaeology was kind of an early discipline in the early 1900s, particularly in the Delaware River Valley, people could, archaeologists were identifying that there were these lithic stone tools that seemed to be older than any of the other tools that we had. However, they couldn't determine how old. It was the Delaware River Valley. A lot of them were out of context. And so it kind of created this problem is, we know they were older, but we just couldn't figure out how old they were. So a lot of, the incorporation of geology into archaeology was having geologists come and help archaeologists figure out the context, whether or not these stone tools were actually in a primary or secondary context, if they had been reworked or moved around, and to determine, how old they actually were. So this photo right here is from the Folsom site, which is the type site for the Folsom Point, a Paleo-Indian point. And so in order to confirm, that this point was actually in direct relation to a Pleistocene age creature, the antique bison, they actually had to have a paleontologist come out into the site and confirm. A lot of archaeologists, they would pick up material and they would bring it into a museum and have it consult, but like the geologists really needed to see it in sight in order for them to be able to say, yes, this is in context. So that's kind of one of the earliest examples of, integration of geology and archaeology. A little bit more closer to home is actually studying mounds. And so here, this is really common, in the Midwest, where we have what we now know are Mississippian age mounds. But before, there was kind of this question of whether or not these were natural features or if they were cultural features. There were a lot of geologists that argued that they could potentially be glacial landforms. So it took actually having, a geologist from the Illinois State Museum come out and participate in the archaeological excavations to document the stratigraphy in a manner that was, appropriate for geology and could communicate to other geologists, and really demonstrate that, based on the stratigraphy, it was not possible for this mound to have been created naturally, that it is a cultural feature. So again, just kind of the early incorporation. And I think you can identify kind of a pattern of archaeologists kind of needing help from geologists to, they have this problem, they're not sure about this, and wanting to kind of confirm something ad hoc or after the fact. I think that's one of the big differences that we see in geoarchaeology today is that, it is geoarchaeology, it's an integrated discipline where they're working a lot more together. So it's not just we need help or we need a consultation. It's that these questions about how humans interacted with the environment and how we can use geologic methods to help answer these questions are really being incorporated at the onset of a project. And I think that's, even clear in my position here as a research geoarchaeologist is a lot of what I do is, incorporating these kinds of questions into the early onset of the projects and trying to figure out how we can do these different types of things. And of course, we need deep testing for the area that we work in because it's a floodplain, which has high potential for deeply buried sites. So they need me in general, but also to help integrate research a little bit better. And you can also see this, all of our national societies, the Geologic Society of America, Society for American Archaeology, they both have geology, geoarchaeology interest groups and geoarchaeology divisions. And we even have our own journal now too, specific for geoarchaeology. So again, a lot more integrated now than what it was in the past. And so I just have some pictures of what life looks like in a day-to-day in the life of a geoarchaeologist. So first, we like to spend a lot of time in the field, particularly in holes in the ground. It's our favorite spot. They can be either hand dug like this one, or they could be machine dug by an excavator or a backhoe. And these are really helpful to help us get a base of what the stratigraphy looks like. And kind of at a very localized scale. Then we would use sediment coring, where we're only collecting a 10-centimeter diameter core of solid earth that we're using to study the stratigraphy. So it's not as kind of comprehensive as having a trench, but it's a lot less invasive and you can cover a lot more area doing coring. So these methods normally really need to work in tandem to get a full picture of what's happening with the stratigraphy. Also, a lot of times you might see people taking advantage of natural cuts, riverbank cuts, road cuts, to kind of get a handle of what the stratigraphy looks like if they don't want to, open up a new hole, because it is destructive. And additionally, something else you might do in the field is to collect sediment and samples from outside of the archaeological site. And this is helpful for us to kind of get a baseline of what outside of the site versus inside of the site looks like for comparison. So after we are finished with all of our really fun field work, we get sent to a basement, say locked away, where we do all of the lab analysis. So what it kind of looks like is this, it's a basement lab. Some typical analyses that we do of soil, loss and ignition, stable isotope analysis might be a pretty common one, particle size analysis, and magnetic susceptibility. Additionally, sometimes with these cores, we would prefer to study them in the lab where it's a more controlled environment rather than in the field. So we would, keep them in these plastic containers, bring them into the lab where we cut them. We take high resolution photographs, we describe them in lab, and then we can also subsample and do other analyses. This is actually a core logger here, which can take 5-centimeter increments of magnetic susceptibility. So some cool toys we have to play with. And then also a lot of geoarchaeologists have an additional specialty in the lab that they work on. Mine is micromorphology. And so what that is this is what the sample is over here. I would take a block of soil that's intact, impregnate it with an epoxy, make it hard like a rock, mount it to a glass slide, grind it down to 30 microns, and then I can study it under a petrographic microscope. So again, it's using techniques from petrographic thin section analysis, but applying them to an archaeological context. Yeah, so that's what the life kind of looks like of a geoarchaeologist. But now we can get into some more specifics of what the research actually is. So I'm going to take you, for those of you that aren't already here, I'm already here, The American bottom is this broad expanse of floodplain in the central Mississippi River Valley. You can see how it's bounded to the bluffs on the on the east, and then it's bounded by the Mississippi River on the west. This yellow star right here is marking Cahokia Mounds. Cahokia Mounds is the largest pre-Columbian sites in North America. We have the largest mound, the largest earthen mound, and the largest mound north of Mexico. It's a UNESCO World Heritage Site, so if you guys are local, I would recommend visiting this time of year and taking a walk, being socially distant, but it's really nice out there. And so you have Monk's Mound here, which is at the very center, and the area that I'm going to be working in or talking about today is the North Plaza. So the North Plaza is, it's an empty space bounded by 4 mounds in each of the cardinal directions. The North Plaza is really weird in terms of understanding the site at Cahokia because it's occupying this really low elevation space. It's called a meander scar of the Mississippi River. You can see the shape of it outlined here in blue. It's a low elevation space where, the Mississippi River used to flow before it's in its current channel now. It's even weirder because at least historically, Cahokia and Canteen Creeks used to flow through the North Plaza. So they would actually kind of flow somewhere around where modern I-55 is right now. But they've since been channelized historically. What that means is if you were to dig or conduct an archaeological excavation anywhere else at Cahokia, you would really only need to go about 30 centimeters to find, good intact features and everything else. In the North Plaza, that's not the case. It's been really deeply buried, and that's because it's in the floodplain of Cahokia and Canteen Creeks. It's kind of the sink of sediment. So historically, it's gotten buried so deeply, you have to dig almost 2 meters in order to get to the archaeology. And so what that means is these mounds used to be much bigger on the landscape. This whole ground used to be much lower. So basically the landscape looked very, very different in the past whenever people were occupying, again, between 10,000 to 1400 AD, than what it looks like now. So part of our plan is to kind of use the soils and the elevations of these buried soils in order to kind of reconstruct what this landscape used to look like when the people who built it actually lived there. Okay. And to do that, we're going to take advantage of the mounds that we have. So again, there's 4 mounds which bound the North Plaza. The biggest is Mound 5. There's also Mound 16 here, it's really small. Mound 15 and Mound 14. Obviously, you can see Mound 5 pretty clear. Mound 14, 15, and 16, not so clear. They used to be a lot bigger, I promise. But again, they've been buried, so they're a lot harder to see in a modern landscape than what they would have been. But anyway, so the point is to use just the toe slope of the mounds. And so the mounds were, constructed on a surface that used to be there. So we want to look at that soil that they built the mound on, as well as the soil that buried the mound, in order to understand how the environment has changed through time. So we're really using that toe slope of the mound as a proxy, just a marker of chronology for when people built it. And we're interested in what happened to the environment before and after people built the mounds. Okay. And so our first excavation here on the toe slope of Mound 5. And then we followed it up with cores to expand the excavation information, the stratigraphy, to the west and to the south of Mound 5, as well as in Mound 14 and into the North Plaza, where we didn't have time to conduct a full archaeological excavation. Then we also did an archaeological excavation on the toe slope of Mound 16. So I've kind of alluded to this thing that I'm calling buried soils. So what is a buried soil? Geoarchaeologists use that term a lot. You might also hear the term paleosol, buried A. What it is, A horizon is topsoil. This is the soil that we live on, the soil that we occupy. It's stable. But if an environment's change or if humans do something, these soils can become buried. And it's a good thing for archaeology because when they become buried like that, they're also preserved in time. So a lot of times that's what geoarchaeologists are looking for when they're helping archaeologists or advising them on where to dig. Is they're looking for these buried soils that could have intact archaeological remains. How they can get buried, again, by flooding, by erosion from upstream, wind blowing in sediments. Again, these are kind of marking environmental changes, right? Because you're going from a stable surface to something that changed and it's no longer stable because it buried it. Also, humans bury soils too. You know, we build up, we put artificial soil on things, and we like build houses and everything. So all this stuff can also preserve buried soils. And just an example of what buried soil looks like, this is a really beautiful one. So this is a nice thick humic A horizon. This is from Mound 16, we'll talk about it later. And you can see the boundary here outlined in orange. This was buried by fluvial sediment. That's why it's a buried soil today. So at Mound 5, like I said, I really just wanted to catch the toe slope of the mound to get that nice contact where you have the mound as a marker and you have the buried soil underneath and the soil that, you know, later buried the mound. I underestimated how much of the mound has been buried. So you can kind of look and you see where my excavation was placed. It really looks like I was at the edge of the mound. It was nowhere near the edge of the mound. The edge of the mound is more somewhere out here, right? So that much of this mound has been buried by historic sedimentation. But we do have that buried A horizon down here, right? So what happened is we had a stable surface. It was buried by fluvial sediment, right? So there's a change from a stable surface into an area that had more active sedimentation because of Cahokia and Canteen Creek, right? No, where's my mouse? Okay, there it is. Right, so this is our sand deposit here. That's the fluvial sediment. And after, you know, all the flooding, they decided to build a mound on top of it. I can talk about that some more, but that goes beyond the point of this presentation. But the key point is that we have this buried soil, and it's about 225 centimeters below the modern surface, or an elevation of 123.09. At Mound 16, we also have a buried soil. So I was a little bit smarter in placing my excavations this time. I learned from my mistakes, but I still didn't quite get that toe slope that I wanted. So here you can see the slope of Mound 16, which again, you know, is still buried. And Mound 16 was placed on top of a buried soil. This soil is discontinuous underneath Mound 16. Again, that's something that we see as people when they construct mounds, sometimes they alter the soil beforehand. But in our excavation we have that does not have the mound footprint at all, we do see this buried soil is still here. And it was subsequently buried by, again, fluvial sandy sediment. And it's really cool because you can see how the sand is just like coming up and like washing up on the mound, which I think is really cool. So you can see how it's burying the mound. Anyway, all of this sediment is filled with clinker, coal sands, and cinder material. So we know that this material was all deposited after settlement. And additionally, we have this material appearing in the top 10 centimeters of the buried A horizon. So that tells us that this A horizon was stable from when they constructed this mound, which we believe to be around 1375. From the time they constructed this mound until settlement period, right? So probably until at least 1850. And that's really cool to see. It's a really nice stable surface that subsequently gets buried by historic flooding. And so we can judge again that this stable surface, whenever people were occupying probably about 100 centimeters below surface, or about 123.88 meters above sea level. Okay. And then finally, we have all of our cores from the Mound 14 area that expanded out upon Mound 5 and in the general North Plaza area. So in total, we collected 43 continuous cores to a maximum depth of 3.6 meters. We analyzed most of these in the lab. 22 we analyzed in the lab, IUPUI. 3 were cut and described in the field. All of the rest of the cores were saved for archives for later analysis. And what we found in analyzing these soils, taking the images, the ISAS, and really carefully describing them is that there's a pretty consistent buried soil. In the North Plaza and Mound 14 area, it's about 200 centimeters below surface, or about 122 meters above sea level. I've been giving you a lot of depths and a lot of elevations, right? So whenever we're working in these holes, like that's what we're talking about all the time is how deeply buried something is and trying to reconstruct what it looks like in our head. But I realized, when I was talking to people, that these numbers don't mean anything to most people. So I tried to come up with a better way to communicate, what I can see in my head to other people. And so I decided to do that with a 3D model. So what I did is I took LiDAR data that's publicly available online through the Illinois State Clearinghouse. And I imported it into, this is a 3D analyst software, Golden Software Server. It's really easy to use, but it's not freeware. So I imported it there, and that's where I get this model, is just from that data, the data set. So this is like kind of the modern 3D surface of what modern North Plaza looks like. So what I did is I took all of that elevation data, I converted this data into, into a grid format, and manually altered the data points based on the core elevations I already had of these buried surfaces, right? So this is the end result of what it looks like. The mounds are, much bigger on the landscape. You actually have this platform underneath Mound 5, which we could see in excavations that you can't see on the modern surface. Mound 16, Mound 14 are much larger than they are in a modern surface. Mound 15, we did not have data for, but I assumed that, it was very kind of relatively equal, equal to how Mound 16 and Mound 14 were, was the assumption. But also, the ground surface in general is much lower, and this slope between, the other parts, South Cahokia to the North Plaza, is much more dramatic. So again, just to get kind of a better image of, what this landscape actually looked like in the past and how people would have seen it versus, how we see today. So what it is, it's really just a visual tool to help people, visualize this data. But like one question that I do get is, why is it so deeply buried in this area? And again, like I said, it's a low elevation area that's kind of a sink for sediment. And some of these things might be related to historic processes and historic land use activities. But also the American bottom is just kind of an unfortunate situation for drainage because it's a low gradient flat area that is surrounded by, steep limestone bluffs. And so this is just kind of a general elevation map where you can see the bluff line is very, very clear, right? Separating the uplands from the bottomlands of the American bottom. And so the problem is, all of these stream channels, they start in the uplands and they flow into the American bottom and then into the Mississippi River. And so they have more competency up here because the slope is greater. So they have more energy, they can pick up soil, they can erode soil, and they carry it to the bottom. And when it gets to that bottom land, it's that low gradient, it loses its energy and it has to dump all of that soil out. Okay, and so dumping all of that soil creates problems for flooding. So there's a serious sedimentation and drainage problem happening in the American bottom. And you can see again, this is where Cahokia is. It's at the confluence of two of these streams. So you can see why, in particular, the North Plaza would be a big sink for all of this sediment and would create some issues related to flooding. One of the interesting things is that in these archaeological excavations, we don't see the signature for high sedimentation prior to contact, right? So whenever these people were living here, we're not seeing the same level of signature that we see post-settlement. And a reason for that is, the urbanization that's happening in the uplands, deforestation, bringing in grazing animals that increases in erosion. But I think one of the biggest contributors to the sedimentation is coal mining. So Canteen Creek, whenever there were early, what is it called? Not exploration. Exploration. Whenever they were looking for coal, the way they found it is they would walk up Canteen Creek and they would find coal seams exposed in the creek beds and they would just start digging it out right there. So all of that sediment was just being, dumped into the creek and it was being deposited down in the bottomlands. And so I calculated it out. It's about 2.7 centimeters of sedimentation per year. And maybe some people don't know what that means, but that's a higher sedimentation rate than some areas of the Mississippi Delta. So it's very, very high. It's very, very crazy sedimentation, and it causes a lot of problems for people historically. So whenever Charles Dickens came to see the American bottom in 1842, he has this quote that few people can exist in such a deadly atmosphere where everywhere was stagnant, slimy, rotten, filthy water. So it was kind of historically, kind of this water world where there's just a very severe drainage problem that made it really difficult for people to live in the area. And I do kind of think that it was probably worse because of the historic land use activities that were happening in the uplands. But in 1905, you have Edward Helm, who was a local engineer, kind of published this cry for a comprehensive system of levees and channelizations in the American bottom, right? Because what was happening is people were trying to develop the area, they were draining the water away from their property, and they were just flooding other people, right? So they needed some sort of comprehensive system in order to develop the American bottom to fit their needs. And so this was done by 1921. So there is the formation of the East St. Louis Drainage Division, which did a comprehensive, across counties system of canals and levees. And so at this point, you would have been hard pressed to find a natural stream system in the American bottom that had not been altered by some way by humans. And again, we can see that this whole area has been heavily altered, not just the hydrology, but the area in general, by urbanization, right? So the American bottom is home to the Metro East, second largest urban area in Illinois. So it's just an image, it's right outside of St. Louis. It's been very, very heavily altered by historic practices. And so this is a twofold problem. First, it's a problem for archaeology, right? Because we don't really know what the pre-Columbian hydraulic system looked like. And this makes it very hard when we want to discuss questions related to human environmental interactions, right? We can maybe get at the human side, but we're not doing a great job understanding what the environment looked like. So we really need to better understand the hydrology before we, completely altered this landscape. And it's also a problem for land managers. So these engineered systems that we've created are static and unsustainable solutions to past problems. So they're not easily adapted to the current problems that we're facing. And so a lot of land managers are now looking to restore natural systems that are more adaptable and resilient to different changes and different challenges. But again, the problem, what did that natural system look like? We've historically over the years altered it so much that it's really hard to make a decision on what should be restored and what really restoration does look like. And so our solution, or also kind of the future work that we're planning on doing here at ISAS, is to make this regional-wide paleo-topographic model for the American bottom floodplain. And what that involves is a lot of work. So the American bottom floodplain, right, it has the potential for deeply buried archaeological sites. That means over the past years, there has been extensive geomorphic investigations occurring related to archaeological problems. It's a lot of great literature, a lot of reports, but a lot of really good work that needs synthesized and compiled. So that's the first step, is compiling all this previous research, figuring out what we've already done and where into like one central system. After we do that, we need to identify gap coverage. So what we're expecting to find is, a lot of concentration of investigations in this area, nothing this area. And that's a problem for creating these kinds of models because you need to have kind of an even distribution of your data sets. So after we compile everything, figure out where we have data, then we're going to kind of identify these areas and conduct additional sediment coring to obtain and to cover these gap areas. And again, what we're looking for is elevations, elevation data of post-settlement sedimentation. That's a hard word to spit out. And it is pretty easy to identify in these cores, again, because like I said, we have coal sand, cinder, clinker material, just filling it up. But if we can't see this in the cores easily, we could subsample these soils and conduct a magnetic fly ash analysis, which is an indicator of coal combustion for energy. So that would be a good marker of what is post-settlement and what isn't. And after we do that, finally, we're going to use this elevation data to remove all this historic sedimentation and to remove the alterations to create what we're calling a new pre-Columbian digital elevation model. So kind of similar to what I made at Cahokia, but it's region-wide. And it's not going to be manually manipulated. It will be done in Esri ArcGIS, and it will be done, the computer will do it. So we'll put in the information and it will create an interpolation model. Sorry, I'm getting too technical. But the computer will do it. So it's a little bit different and it's a much bigger scale than what I did before. So after we have this new digital elevation model that represents the pre-Columbian landscape, we're going to conduct a watershed analysis. And what that will tell us is it will tell us where water used to flow based on the past topography. And so what we're hoping for is when we get this all done one day, we're going to make these data sets open access. so that these models can be utilized by other researchers, by other land managers. We've already talked with other researchers and land managers, and there is interest in people using this for their own purposes. For instance, there's geographers who would like to use these data sets to model how the Mississippi River used to flood and which areas it would have flooded first. And again, like I said earlier, it's land managers are having a hard time kind of deciding or justifying what should be restored. So we're hoping, again, this can be a baseline for them in their management strategies. It's like a justification of this is what we can restore, this is what we should restore. So really just hopeful it can be useful to lots of other people. And ultimately, it's really just a baseline, you know. We have so many more like bigger questions about, you know, how past people altered their environment. But first, we really need to get a grasp of what it used to look like. And that's all I have for you today. And I think we have time for questions, and hopefully you've been sending some questions while I've been talking.
Thank you, Caitlin. That was wonderful. We have one question so far, so I'll go ahead and ask it. This comes from Michelle. How can you know if the land was dry if the water has been diverted, resulting in previously dry archaeological sites having been washed away or mostly destroyed?
So are you asking about the lack of data, or that sometimes data can be washed and removed? I mean, so one approach that people do to kind of understand, so like the lack of record in the stratigraphy, I think is what you're asking me. Sorry if I don't understand the question fully. I mean, one method, you know, we're using is instead of doing these terrestrial cores, people are conducting or collecting cores in low-lying areas that would collect sediment rather than have it eroded. So an oxbow lake would be a good example of where the sediment would be collected rather than eroded away by later floods. I think burrow pits too could also be a potential area of collection. I'm sorry if I didn't answer your question.
We'll just move on to the next one unless Michelle wants to clarify or if there's something else she wants to know. A couple of people mentioned the date of 1375 for the North Plaza. Does that refer to the initial construction of it or its abandonment?
Sorry, can you repeat that?
1375 as the date for the North Plaza?
Yeah, it's based on the material culture. So the ceramic is dating to Starlight phase. And it might be an addition. So it's possible, because I was at the very edge of Mound 16. So it's possible that could have been a later addition to the mound. It doesn't necessarily represent the beginning stages of the mound because they could have been constructed in stages. So I just got the very edge of it.
Thank you. Tim wants to know how fine-grained can you get in terms of events with micromorphology and geoarchaeology?
That's a good question. I mean, I guess it depends on how you're asking me about Mound 51. Is that what's happening? It's really weird to like answer these questions and not see people's faces, just your pictures. Are you asking me? I feel like you're asking me whether or not we can get kind of seasonality. Okay, so one really cool thing that I had in the micromorphology underneath Mound 5 is an incipient A horizon that is about, oh my gosh, maybe about like 3 millimeters thick. And that was really cool to see because it just like represents this like little sliver of stability in between. So, you know, it does tell us that there are these moments of like hiatuses. But in terms of like parsing out, like this was between, you know, 5 or 15, it's a little bit, it's hard to do because especially like soil formation, it depends on so many different things. It's hard to, you can't just say like, we have like kind of a baseline as, you know, we say like 5 centimeters of soil is 100 years, but like that's in a very specific kind of environment. Right, so there's so many different factors that can impact how quickly a soil forms. that, it's hard to kind of, say this is a measurement and that means that it took this many years. So I think, it needs to kind of really be in tandem with some other kind of datable material that's coming out of it, is my answer. I think we can do something with that pit because there's so much material in it, but I'm not totally sure how to do it yet.
What has your research in the North Plaza revealed about flooding during the Mississippian period? Is there any evidence for that?
So what it has told me is, there is evidence of flooding happening before they constructed Mound 5. So we do have evidence of, people living on this stable surface, that A horizon, that was subsequently buried by flood deposits, but the response of people is to build a mound on top of it. So, I mean, yeah, we do have evidence. I see some terrestrial evidence of flooding occurring, but I also see evidence of people returning and investing in the space after floods occur. So I guess I'm just seeing resilience to flooding. That's the evidence I see just in the terrestrial work that I've done myself.
We have a follow-up clarification from Michelle about the dry versus wet. So she's wondering, say in the Mississippian period, you're saying it's dry where the mounds were. So what happens later on when rivers change course or creeks change course, and maybe that wipes out some of the evidence of sites that used to be there?
Oh, I don't think it was dry there, that North Plaza. I think it was a wetland. It was probably mostly inundated for, most of the year. And that's, based on an entirely different data set that I haven't presented on today. But no, so I don't think it was wet. Also, it seems like the floods that do occur in that area, like I said, it's kind of a sink for sediment. So, there are some major floods, like when the Mississippi floods in different areas, it's eroding. But in that area with Cahokia and Canteen Creek flooding, it's not necessarily removing stuff, it's rather depositing sediment. So it's burying things instead of removing things.
Okay, from Tamara we have, can the sediments tell you about the duration of a flood or its magnitude?
Yeah, there are people, again, you have to be aware that materials can be removed in different floods. So again, it's about, finding those sink areas where you're more likely to have deposition rather than erosion. So whenever people are studying, paleo flood magnitude, they're looking in places like Oxbow Lakes. Out in Missouri, this is a cool one. I saw they were experimenting with sinkholes and like identifying flood sediments that were preserved in sinkholes. Sometimes, they might look like behind, like really, it sounds weird when you say it. It's kind of funny to see. It doesn't sound very scientific. They look behind big rocks because, basically don't get washed away because the rock is like blocking the sediment. So they get like kind of preserved behind rocks. So you have to be careful about, finding areas where these sediments are going to actually be preserved. Right. And again, like those flood sediments too, in part at Mound 5 in part are preserved because they put a mound on top of it.
We have another question. Why is ISAS a good place to do this kind of research?
Geoarchaeological research?
Yes.
Well, the American Bottom Field Station where I work, I think it's an awesome place because we have such a high density of archaeology. And then also, we are working in a floodplain of the Mississippi River, so the potential for buried sites is very high. So in that sense, it's a great place to do archaeology.
We're slowing down on the questions now, but one did just trickle in. Why should your listeners care about geoarchaeology?
I mean, I guess it depends on where you're coming from. If you're an archaeologist, why should you care about geoarchaeology, or just the person in general? For a person in general, I say, at least what I'm involved with in geoarchaeology is what we call climate change archaeology. So it's this idea that, you can use the past to help inform strategies of the present. And so a lot of what I do, like I've actually participated with the United Nations, working as kind of a consultant for least developed countries on loss and damage, right? So cultural resources being something that are a loss and damage from modern climate change. But I think, that key in kind of using the past to inform the present is, the geoarchaeology is integration of, geologic methods to answer anthropological questions. And I think, the sense of integration is having the ability to work at the right scale to answer some of these questions. And again, to kind of work in current theories where you're using what the coupled Earth systems, human Earth systems model, where we're understanding that humans are both altering and responding to changes in the environment. So it's not just, a one-way street, but it's a cycle. And you need to kind of understand both things. So I think the most important part is understanding the scale at which you're collecting data and making sure it's a scale that's actually relevant to, human societies.
Good answer. I think that's it for our questions. So I'm going to share my screen one more time.
I'll stop sharing. Or
So thank you again, Caitlin. Let's try this. And thank you everyone for joining us today. Our next lecture is on December 4th at 4 p.m. and it's entitled Tracing the Angel Axis, Architectural Alignments and Lunar Landscapes in Southwestern Indiana by Dr. Elizabeth Watts-Maluhos. So we hope you can join us again, and I hope you enjoyed yourselves today. Thank you.